website, and it has ads on it. Any questions sort of about the format of the exam? How we're gonna conduct the exam? We'll be in this room, assigned seating. Come in, there'll be a seating card on the door. You'll have the entire hour and 20 minutes to complete the exam, but I don't think you'll need that time. It'll be about 50 questions, multiple choice. You will have a few calculation problems, but I'll keep the numbers very, very simple. Practice them. There are examples in the old exam. Okay? You can ask me questions during the exam. If something's just not clear, then you can ask me. I'm not going to give you any special information, but I might be able to clarify some language. And if there is special information needed, then I'll tell the whole class. So feel free during the exam, if you have questions, you can ask me. No questions then? No? We're all good to go? All right. Well, I'll be around if you want to see me. I'll be available today, tomorrow, Monday. Just drop by. Send me an email if it's not during my office hours. We're going to finish up this chapter today, and then we'll also probably move on into Chapter 3, but Chapter 3 will not be on the exam. All right. So the lungs bring oxygen to the blood. From outside air. And we've talked about this, but Boyle's law describes how air comes into the lungs. The lungs expand. Remember Boyle's law, PV is constant. And so if V gets big, that means that the pressure inside the lungs, pressure decreases inside, and so all that high pressure air outside of your lungs will rush into your lungs. So if the lungs expand, that increases V and decreases P, so the air rushes in. The lungs are not muscles. Right, the lungs are just sort of bags sitting inside your chest. They can't contract or expand on their own. Instead, the diaphragm or the muscles around the lungs contract and relax. To open the cavity. The iron lung, I'll show you a video about the iron lung. But the iron lung was once used with polio patients because their muscles get really weak when they had polio, and they just weren't able to breathe. Those muscles that were around their lungs weren't able to expand their chest cavity or make their chest cavity smaller, and so they had to have help breathing. And so the iron lung was a cylinder that was about human size, because there was a person with their head sticking out and the rest of their bodies inside of the cylinder. So their arms and their legs and all their body would be inside the cylinder. And what the iron lung would do is it had a compressor on it, or it had this diaphragm that would move in and out that would cause the pressure to increase and decrease. So the iron lung caused the pressure, that is the pressure inside of the canister, and when the pressure inside of the canister is high, what does that correspond to? Exhaling or inhaling? If I have a high pressure inside of the canister, what's going to happen to my lungs? What am I going to do? Am I going to exhale or inhale? Now remember, my head is outside, right? If I have a high pressure inside the canister, I'm going to exhale. That high pressure here is going to compress down my body. It's going to squeeze all the air up out of my lungs and into the air outside. So high pressure inside, that corresponds to exhaling. And then a low pressure inside the iron lung, that corresponds to inhaling. I know that that's opposite what we talked about before, but remember what we talked about before was the pressure inside of the lungs. So when I have a low pressure inside of the lungs, that is when I'm inhaling because the high pressure air is coming out around me. Oh no, it's the same. Yeah, never mind. That's right. Okay. So anyway, that's how an iron lung works. Let me show you a video. It has sort of a more detailed description. It shows a lady inside of an iron lung. The outer surface is this part right here. We'll see in a later chapter that that's, even though we call something else the lens, that's the part that actually refracts the light, that bends the light the most. The aqueous humor is the fluid that is like right here. We'll have two different types of fluid, the aqueous humor and the vitreous humor. The aqueous humor is in between the cornea and the lens. This is replenished. And it drains. And you'll see that that's in contrast to the vitreous humor. So it's the liquid fluid that's right here, and it's continually replenished. It brings nutrients to the eye and takes away waste from the eye, the aqueous humor. The lens focuses light onto the retina. The lens is right here. The lens of the eye is kind of cool. Again, we'll talk about the lens later. For now, I just want you to have an overview of the eye. But the lens is an adjustable lens. It can stretch out or it can squish down so it's wider in the middle. And that makes us able to see things that are really far away and then also things that are up close. Most optical instruments that we have just can't do that. Right? Because if you have a camera and you want to change the focus of your camera, you have to alter the physical configuration or alter the lens. But that's not true with the eye, that the eye can actually change the shape of its lens. And then it lasts for like 80 years too. The vitreous humor, this holds the spherical shape of the eye. It's the fluid that's in here. This is the vitreous humor, and not replenished. It means you pretty much got the same vitreous humor that you were born with. The liquid that holds your eyeball into its spherical shape, you keep your whole life. Pretty much. Your eye changes a little bit as through your childhood, but mostly your eyes are about the same size as when you were born. That's why babies look like they have what? Big eyes. That's why they're so cute. Right? Unless they're pooping all over you, and then they're not cute. But their eyes are bigger than they really need. And then the retina is detects the light. And the retina is sort of this part of the eye, the back part of the eye, where the light focuses and it converts that light into an electrical signal that goes to your brain. Again, a lot more about the retina and the lens and all those light gathering parts of the eye in chapter 7 or 8 or whatever it is. Okay? But I want you to know the parts of the eye, especially these parts, and then know particularly about the fluids in the eye and the problems that you can have. You ever been to the eye doctor? Yeah. A tonometer is used to measure pressure in the eye. It tests for things like glaucoma. Is the pressure of the fluid in your eye too big? That can occur if that drainage of the aqueous humor, if it gets blocked in some way, or if your body is producing too much fluid that goes into that. So there are a variety of things that can cause glaucoma. The tonometer, I'll show you a video of a tonometer, but it's that little thing that your optometrist use, that little puff of air usually. Right, done that before, you know what I'm talking about, those of you that wear glasses. Yeah, so that puts a little tuft of air onto your eye, and it measures the pressure. What's that? Yeah. Let me show you one. I have a video of a veterinarian. They have to do the same thing, right? Veterinarians do a lot of the same stuff as human doctors. But this is a tonometer. Oh, let me finish this. It measures the the force required to bend the cornea. And that gives you a measure of the pressure in the eye. Yeah. I tell you what, I had my first optometrist visit a few months ago, and it was not bad, but I didn't like the tonometer at all. Let me show you this. This is a canine tonometer of air. You can ask your optometrist next time to see if they can, instead of doing the blast of air, if they can just hit your eyeball with a little plastic pin and measure the pressure.
I mean, it's not like that, but now they just run a thing over the system.
Oh, really? Huh. It hurts.
Oh, yeah, it's flat.
All right. The Aqueous Humor. That's the fluid between the cornea and the lens. Remember, the aqueous humor, here's the cornea, here's the lens. The aqueous humor is sort of right here in between those two. Is replenished if the drainage is blocked. The pressure becomes too big. And that can damage the optic nerve. What's this called? High pressure? Glaucoma, right. All right. You can either reduce the production of the fluid, that might be the issue, that you're just producing too much faster than it can drain, or you can have surgery to actually open up those drainage ducts to make them drain more quickly, depending on what your problem is. All right, the brain, we have several protections for the brain. The skull, of course, we have our cranial and our facial bones. The meninges. Am I saying that right? Meninges? Really? I'm sure they're right. These are three membranes that cover the brain. And these contain CSF, or cerebral spinal fluid. And the CSF acts to cushion the brain and regulates blood flow. You have about 3/4 cup of CSF in your head, and that's about 300 or 150 milliliters. A half cup of coffee around your brain that protects it from damage. Problems can occur with production of CSF. I'm sorry, this wasn't supposed to be here. Are the lack of production. Either you can have too much or too little. And this creates pressure in the cranium inside the head, and that's called inside cranial pressure. Hydrocephalus. That's an abnormal accumulation of CSF, so too much CSF in the brain, or around the brain rather. And a lack of CSF can also cause problems. The brain can bump up against the cranial bones, and that can be really painful, of course. All right, so know what CSF is, know the three protections for the brain. I'll just sort of go through your notes as I'm making up your exam and pull questions directly from your notes. Okay? I have a little video about CSF. It's really just an animation, but it sort of shows that fluid and what it does. All right, let's see. And then finally, or a couple more things, is the bladder and then the bones. I think we'll be done with this chapter. So the bladder can hold about 500 milliliters. Or more of a fluid. You know, a 400, I guess 500 milliliters, that's a flask about that tall. So it can hold a cup about that tall. When it reaches about 200 milliliters, 500 is roughly the maximum that it can hold. When it reaches 200 milliliters, the person feels an urge to go. You know what I mean? Like to go to the bathroom. They feel this urge to go because of the nerve signals given to the brain at this pressure. Now, eventually this goes away. So like if you feel like you have to go, if you just wait, then you won't have to go anymore. Because you don't really have to go with 200 milliliters. You still have another 300 milliliters that you could fill up. But if you add the other, if you add another 200 milliliters or so, then the urge comes again. This pressure for this urge is is 30 centimeters of H2O. Or if you want to talk about this in millimeters of hydrogen, of mercury, like we do with blood pressure, it's 22 millimeters of mercury. Remember, atmospheric pressure was what? About 20, it was 760, so quite a bit, a pretty small pressure. Pregnant women feel a greater urge because of outside pressure. You know, because there's a human being in there kicking around and stuff by the baby. And this external pressure, it just increases the pressure of the enclosed fluid in the bladder. We talked about this earlier. This is an application of which principle? Right, Pascal's. That if I apply a pressure to an outside container, then that pressure is felt all the way throughout. So if a baby pushes on your bladder with his foot, his or her foot, then that pressure will be felt throughout. And I'd be prepared for those types of questions where I ask you, okay, this situation, what is this an application of? What principle is this an application of? Oh, this is supposed to be a question, but it's an application of Pascal's principle. All right, and then finally, bones. We talked about stress and strain. Remember, stress causes strain. That stress is kind of like pressure. It's a force per unit area, and it causes some deformation in the material. It causes the material to stretch, or to shear, or to break. And so stress and strain are related to one another. Stress is a force per unit area. That is F over A. And then strain is a deformation of the material. When I say deformation, like I said, I could mean a stretch, like a rubber band stretching, a shear, a break, some strain in the material. Stress causes strain. Bone mass density measures the strength of bones. And it usually peaks in a person in their 20s. And osteoporosis, bone density is reduced and more susceptible to breakage. Okay? That's easy enough, right? Those few topics. Just it's easy if you know it. If you don't know it, it's not going to be easy at all. But if you know those things about these various topics, the bladder, the brain, the eye, the bones, know how these things will apply. Let's try some of these questions. We'll do the one up here, top left. The tonometer is used to measure pressure in which of these places? All right, let's stop at 23, 24. Awesome. C is right. Let's try the one on the right, the brain and the central nervous system. What is hydrocephalus? What is that a result of? All right, we'll stop at 23. All right, B is right. Hydrocephalus is too much CSF. Where do you find a dog with no legs? Right where you left them. All right, we'll try the glaucoma question here. It's the result of what? All right, let's stop at 20. Okay, A is right. High pressure in the aqueous humor. You can't really have I mean, I guess you could have a high pressure in the vitreous humor, but it'd have to be corrected early on because you have that your whole life. And then what part of the eye is continuously replenished? Let's stop at 15. 15. Okay, he is right. The aqueous humor. What else did y'all put? B and C. Now B and C, the cornea and the retina, those are just sort of parts of your eye. They're not really replenished at all. But make sure that you understand the difference between the aqueous and the vitreous humor, okay? And what they do and the different purposes they serve. What do you call a guy with a car on his head? Jack? Did she say the answer?
I said carpet.
All right. Let's move on. We're going to move on to chapter 3. But again, not on the test. All right. We'll probably have a quiz on chapter 3. Y'all want to have it on Thursday? A quiz on chapter 3? We'll probably have the quiz the following Tuesday on the first part of chapter 3. Is Mo better? More quizzes are better for y'all. I guess better to have it on Thursday. But I understand. So in this chapter, we're going to talk about energy. We're going to talk about the different types of energy, kinetic and potential energy, and the energy of motion. And you might think that's kind of silly, but it's all underpinning in how we begin to talk about the energy using, or the body using energy. So, our body's metabolism, just how our body uses up energy to do various things. So these initial things are kind of important to understand, kinetic energy, potential energy, and the like, as we move into looking at the body. So energy is the ability to do work. But look, work is not really what we think of as work. Like work has a particular physics definition. And when we're talking about work in a physics sense, with a particular physics definition, work is done when a force causes a displacement. So work then is equal to the force times the displacement. I have to have both of them. If I have one without the other, then that's not work done. So if I push on this thing, I'm applying a force to it. I'm not doing any work on the object. Even though I'm applying a force, I'm not doing any work at all in the physics definition of what we call work. Or if I have something that's moving, but there's no forces acting on it, which can also happen, right? That Newton's first law, that an object, if it's in a current state of motion, it will continue in that state of motion unless a force acts upon it. If an object is moving without a force acting on it, then there's no work being done on that object either. You have to have both the force and the displacement. If you want to think of displacement, I don't think we'd really define displacement. If you want to think of distance, that's fine too. That an object has to move from one position to another. But I'm going to stick with displacement. I think your book uses that term. If an object has force but no displacement, there is no work. And work, or displacement rather, d, is just a difference in the final and the initial positions. I'm just moving an object from one place to another. So, if an object's moving, then it must have had at least work applied to it at some point. Right? If an object is just moving through space at some speed, at a constant speed, then there must have been something that made it get up to that speed. At some point, we had a force that acted on it over a distance, and that's what's causing it to move at a certain speed. As I said, work is the product of the force and the displacement, but in particular, it's a product of the component of the force that's in the same direction as the displacement. We talked about components some time ago, back in chapter 1. So if I have a force that's in this direction, then we talk about x and y components, then that means that I have a component of that force that's in this direction and a component of the force that's in that direction. I have both an x component right here, and I have a y component. These make up the triangle that are that vector, right? So if I move the vectors around like this, the f is right here, fx, and fy. I can break that vector into its components. Remember we talked about how I can move from this point to this point, or I can move in this direction and in that direction. And that's the sum of those two vectors is the same. So that vector of f is broken into its x and y components. And our work is the component that is in the same direction as the displacement. I'm going to put it as fx, assuming that our displacement is also in the x direction. But a more general term for this, you don't need to write this down, but you might recognize this if you remember any of your trig from high school, if you did geometry or trig. The x component of that force is equal to f times cosine theta times x, the distance that it travels. This vector right here is equal to f times cosine theta. If that makes sense to you, that's great. If not, that's okay too. Don't worry about it. You don't even need to write it down because I won't test you on it. Okay? But what I will test you is that not all of this force does work. It's only the part that's right here. So if I'm pulling an object, like this, part of the force is pulling up, and part of the force is pulling horizontally. And it's only the horizontal force that's causing work, because the thing's not moving vertically, right? Y'all follow me on that? That you have to have displacement in the direction of the force in order for that force to be doing work. So if the force is in the same direction as the displacement, the work is positive. Let me just write this down, and then I'll explain what this means. If the force is perpendicular to the displacement, well, what is that work being done? It's nothing, right? The work is 0. If it's perpendicular to the displacement, the force is in this direction, or rather, the displacement is in this direction, but the force is in this direction. That's no work being done at all. And if the force is in the opposite direction as the displacement, then the work is negative. Work is a scalar quantity. What does scalar mean? We saw that back in chapter 1. We had scalars and we had vectors. And scalar quantity, or vector quantities, have a magnitude and a direction. That's the special thing about vectors. But what is scalar quantities? Only a magnitude, right? So scalar quantities only have magnitude, like time is a scalar quantity, mass is a scalar quantity, charge, scalar quantity, as opposed to forces, vector quantity, velocity, vector quantity, displacement, vector quantity. So we have these different types of scalar and vector quantities. And work is a scalar quantity. That means no direction. Only magnitude. However, often with vector quantities, we use these signs, positive and negative, to indicate direction. Like on your XY coordinate system, to the right is positive, to the left is negative. And so often we use signs to denote direction. But that's not the case here. The positive negative for the work does not give direction. Instead, it talks about, do I give the system energy or not? So the sign of the work, whether it's plus or minus, indicates whether the force gives or takes away energy. So positive work, I'm going to give energy. Negative work, I'm going to take away energy. So let's imagine, let's say that I have an object that's sliding across the floor. Like this. I'll push it this way. So it'll be sort of like the positive way. I'm pushing this desk across the floor. There are a couple of forces acting on the desk. There are actually several forces, right? There's the force that I'm pushing in the horizontal direction. There's another force that's pushing in this direction. Which force is that? So the normal force is pushing up. The frictional force, so normal friction, the applied force, that's the Chad force, I'm pushing, that's my force. Did y'all know that? Yeah. And then there's one other force, what's that? What? Huh? Oh, the net force is like the sum of all those forces, but no? The gravitational force, yeah. So if I have a block that I'm pushing, say it's going in this direction, so my displacement is in that direction, I have several forces acting on it. I have the gravitational force, weight. I have the frictional force, F. I have the normal force, Fn. And I have the force, Chad. Now each of these we can think about the work that's being done by each of these forces. If it's moving in this direction, what's the work done by this force? Positive, negative, or zero? Zero is right, because there's no displacement in the direction of the force. So this force has zero work that's been done by it. Similarly, what about this one? What's the work done by this force? FW, zero work. What about F, Chad? Positive work, because the force and the displacement are in the same direction, and so it has positive work. And this force, the frictional force, negative. And so if I have the frictional force, it's going to act to take away energy, which makes the chair stop. Right? It takes away energy. That's what the frictional force does, because it is opposite the displacement. So if I think about the works here, I have a negative work, positive work, a work equals 0, and a work equals 0. And then we can also just remember that this force, this applied force, was actually a force that was like that. And so there's an extra force here that does no work at all. Right? So that force, if it's applied at an angle like this, that there's actually two components to it. And one does work and one does not. All right, let's try this, the clicker question. Each of these moves to the left. So my displacement is moving in this direction to the left. And then these are forces that are acting. Now there might be other forces acting on these blocks, but these are the forces that are acting. And the first question is, which force does no work at all? A, B, C, or D? In which of these situations is the force doing no work? All right. Let's stop at 42. Very good. A is right. The one that does no work is the one where the displacement, x, and the force are perpendicular. So A is the right answer. Which force does positive work? I'm sorry, which force does negative work? Yes, number 2. All right, let's stop at 30. Okay, seems a little trickier, right? Because I know what you're thinking. The force that does negative work, well, this force is in the negative direction. So shouldn't it be this one? I don't know. I'm sort of confused about which one it is. It doesn't really matter the direction of the force. All that matters is what is the direction of the force relative to the displacement. So negative work occurs when the force and the displacement are in opposite directions. Positive work occurs when they're in the same direction. But negative, they have to be opposite one another. And so here, if x is to the left, which force is to the right? That's the answer. C. Right. So C is the right answer. All right, so the one that does negative work is C, because F and X are opposite. I'm not going to show you 3 or 4. I'll tell you what they are. But 3 actually has 2 answers, right? What are the answers for 3? B and D both do positive work. B and D. And of those, let's do number 4. So of B and D, which of those, between B and D, which of those do the most work? Now I assume the vector is the same length. I'm not sure that it is in this figure. But the vector here is the same magnitude as the vector here. Which of those forces do the most work? Is it either B or D? they're the same magnitude of force, right? Say they're both 10 newtons, and I want to know which one does the most work. Ask your neighbor what they put, okay? You mind? Or tell your neighbor what you put. Everybody tell them? You tell everybody? All right. I'll stop here at 105. 105. It got worse. Like when I asked y'all to ask your neighbor, it just got worse. The answer, the one that does the most work is B. Because remember, this force is actually broken into two parts, and one does zero work. Ow. Its work is equal to zero. And then the other does positive work. Okay? So remember that if I have a force that's not acting in the direction of the displacement, I can either have negative work or I can have... Yeah.
So on our test, like, if you have a question like that, are you going to give, like, which one's going to be the X and which one's going to be the force? Because, like, that line is not drawn there. Like, you know what I'm saying?
Oh yeah, I'll tell you. Well, I did tell you. I didn't draw X here, but I told you that they do move to the left.
Okay.
But no, I wouldn't necessarily draw the X vector, but I would tell you what direction they're moving. And I would expect a question. But not on Tuesday. Right?
Oh, yeah.
Right. Okay. We already said this, but it's worth saying again. Negative work takes energy away, and positive work gives energy to an object. All right, we'll do these last two clicker questions. Is it possible to do work on an object that remains at rest? Is that possible? If you have an object at rest, can you do work on it and have it remain at rest? All right, let's stop at 23. 23. The answer is no. Because look, work is equal to F times D. In order for an object to have work done upon it, it has to move from one position to another. And if it's just staying in the same position, there's no work. So if D equals 0, that means work is equal to 0. I can still have forces acting on it. I'm trying to push this, I'm applying forces to it, but it's not moving. Even though I'm exerting all of this force, I'm not doing any work on the object. This is really just sort of a physics definition of work, right? Like, we don't always think of that in the same way, that my muscles can become exerted even if they're not moving, right? We call that, do y'all remember what that was called? Isometric contractions, right? A box is being pulled across a rough floor at a constant speed. What can you say about the work done by friction? Does the friction do no work, positive work, or negative work? All right, let's stop at 32. 32. Okay, C is right. Friction will always do negative work because almost in every case, friction will oppose the direction of motion. It's every case that we're ever concerned about. It will always oppose the direction of motion. I will stop there. And I'll see you all on Tuesday for the exam. Let me know if you have any questions between now and then. Okay, I'm available to help you. Valentine's